Oh, that's not a good idea. Discrimination one, there are too many leftovers. It's going to be bad.
Here, one of them. Come on, if you got it.
Come on.
Bro, why would Curry help you out? Just stay on, that's not coming throughout the week.
No. I understand. I have one thing that we
I don't want to take part of the one.
let's take part of the line.
I'll take part of the one, it's not.
See? Innovative here.
Yeah.
And stop.
Ah. Yeah, go on anyways.
Oh,
End up eating the whole thing, but.
I only get 140. That's still honest.
Richard. Did you get it? Which one? Did you get the update? Yeah.
No, only 7 o'clock.
No.
Fast? How's it going, Terry? No. Yeah.
Yeah, keep on
But I haven't read the big one, just so I don't feel it.
I'm too long.
Yeah.
Yeah, it's a very good suggestion. Don't just give this for our, but. You know, yeah, I guess you. Or even the trajectory, like, maybe we're following, set the double, but to see if there's no good that you got. Like, if our was trying to make that's not, like, no, I'm sorry. The whole thing, the whole time. Or. Or that, that should be already. I already. Oh, blackness.
That's exactly what I was going to do. Go get that. Okay.
I'm not sure all the.
I tried to plug us.
No, it's really good for yellow that you get. But. What that does for your. Yeah, that's great. Yeah.
Yeah. Down there.
Yeah.
I'll. Well, I'm not really good. Pero the mic.
Oop. Oh, damn.
And the public will be able to go back like in.
All right. You want to go ahead? Get the mic. Yeah. All right. Welcome everybody to another week of the Embodied Intelligence Seminar. Today we have Rob Platt. Rob's a professor at College of Computer Science at Northeastern University, and he's currently spending his time with the AI Institute just down the street. So before that, he was a technical lead at the NASA Johnson Space Center, and he actually was here at MIT as a research scientist. I don't know how long he was, but but we all know him from his famous paper on too long. That's right. Belief space planning, and likewise, he's currently very interested in developing robots that perform complex manipulation tasks in a very uncertain everyday world. So welcome back, Rob. Let's greet him back with a round of applause. Yeah.
Thank you very much, Terry. Hello. All right. So so I'm Rob Platt. I'm a professor at Northeastern, and along with Steffi Telex, I'm a team lead at Boston BDAI. So I guess if you're a first year grad student, you could be forgiven for thinking that the thing to do right now is to stop whatever you're doing and install a VLM on your computer and download a bunch of data and train and adapt it for this was the thing to do, and indeed. That's the thing that a lot of people are doing is basically building large neural networks to learn, to learn robot behaviors using very uncommitted models. So, right, this is parameter count over time. Bigger models, more data, more money. And I guess like from a robotics perspective, the question is that what we should be doing here, because it's clearly what's been successful in, say, NLP. And I'd like to point out the very excellent work of OpenX embodiment, which is essentially that's the biggest thing going in this direction. Let's say so we have RT2, which is a VLM, which is adapted to some robotics applications. We're going to collect as much data as we possibly can, and it's a little clunky, difficult to do that, but that is clunky and difficult to collect the data. But that's the approach. And I guess that's a really exciting project. I just want to point out a couple of obvious maybe just one obvious drawback, which is the significant domain shift that exists between whatever the data set is that you've used to train the model and whatever your application is. So, your robot domain is obviously, is almost certainly going to be somewhat different from whatever that training data was like. And furthermore, the tasks are going to be different too. So at least at OpenX, there's a pretty small number of tasks for which we actually have a significant amount of data. So it's something to think about. So even if we're taking this big data approach, you need to really think about the problem of how to adapt the model to a particular setting, and to adapt the robot control policy to changes and in your environment and just the unique things about whatever environment you may be in. Right. So when I think about this problem about adapting the large model, I sometimes think about it in terms of this this paradigm. The big small, so it used to be like prior to, let's say, 2015, that when people were talking about robotics, they were actually talking about the thing on the left, where we had a model and we ran a perception system and we populated the model, and the model represented what we thought the environment was, and we had a planner that told us how to act given the model of the environment. This is model-based robotics. And on the right side of this slide, of course, we have the big data approach. Oh, there's like a huge lag in my slides here. What I'm going to do, I'm going to try restarting my slides. Is that okay? Let's see. And if that doesn't work, I'll restart Zoom. Okay, so yeah, model-based, model-free, you get the picture. Model-free, from a machine learning perspective, you can think about this as bias versus variance. The thing on the left is like way biased. It's like biased with some like the most complicated model that you've ever heard of, and the thing on the right is like it's also more complicated than anything you've ever heard of, but it's totally uncommitted. Almost no data to fit the thing on the left. And a lot of data through the thing on the right. And of course, the question is, damn it, it's happening again. We want to, right. Imagine that you can see that thing on the, all right, I'm going to kill my Zoom session. Actually, I'll stop the share and I'll reshare. See if that works. I still have my problem, but all right. I don't know. I'll try to ignore it for a little while. See if that works. So we want the thing we want to do something in the middle between these two extremes. All right. So we want something that is structured. We want to do something like model free. Insofar as it's uncommitted, but it has more structure. So the problem with the model-based approach. The problem with the model-based approach is that it is, very brittle because there's too many assumptions made by the model. So we want something like model-free, but we want we want additional ability to adapt. So our approach is going to be to constrain the neural network model. We're going to encode symmetries that we believe exist in the environment. We're going to code that into the neural network model. So this is, the question about how to fill this middle box, that's been like something I think folks in robotics have been really interested in. And it's just been a very hard nut to crack because the obvious things you would think of, like taking the traditional algorithms and like, doing the end-to-end learning through them, like doesn't seem to work very well. So this thing is something that this symmetry structured, what we're going to do is we're going to take the neural network models and we're going to encode constraints into them reflecting structure that we believe exists in the environment. So what kind of structure is that? there's, I can kind of see that there. So here we have this tabletop manipulation domain where notice that on the left-hand side and on the right-hand side, roughly the same thing is happening. So on the left, we've got, it's pushing this block up and down, and on the right, it's pushing this block side to side. It's the same behavior. It's just like modular rotation, okay? So thinking about that slightly more formally, we have this picture. So the state here, imagine, is a top-down image of the environment. This is an example. The action, let's say, is a velocity in the plane. And the symmetry in question, let's say, is the group of SO2 rotations. So the thing on the right is basically the behavior that you see on the right. That's basically like a rotated version. So it's like, and the rotation, that's like the G, applied to S. That's like applying the rotation to the state, which is rotating the image, and likewise with the action. So the intuition we had on the prior slide about the top-down block pushing and the side-to-side block pushing being the same, modulo a rotation. Another way to think about that is that the transition dynamics are invariant with respect to this rotation, to planar rotation. And that constraint is what I've written here at the bottom of the slide. So the transition dynamics, like you see it on the left, it's like S prime, this is the probability of getting to S prime, given you took action A from study. You see this. So on the right, it's the same thing, except they're all rotated. So, obviously, the probability of the thing on the left happening is it should be the same as, according to Newtonian dynamics anyway, it is the same as what's on the right. So there's something about physics that physics told us something about the symmetry environment, that told us something about the transition function, this symmetry that exists in the transition function. Here, we're thinking about the plane. We're thinking about the group of SO2 rotations. It doesn't have to be those particular things, though. It could be SO3. It could be translations. It could be reflections. It could be scale. It could be other stuff. The situation that we're addressing, though, is the situation where there is some kind of there's an invariance in the transition function, a known invariance in the transition function with respect to some algebraic group. And that's interesting because this idea has actually been known, like in a pretty general form, for quite some time. But it's not too hard to prove these to prove this thing. It basically is saying that if the transition function is invariant in the way I showed, that the optimal Q and the optimal Q function, the optimal value function, and the optimal policy are also invariant, or the optimal. Oof, sorry. Oh God. Yeah, it's I don't know, maybe I should just hang up or something. Q function is invariant. The policy is equivariant. I'll tell you what that means in a moment. But the point being that when the symmetry exists in the world, we know that it also exists in the solutions. The symmetry exists in the problem. It also exists in the solutions. So what we're going to do is we're going to use an assumption to constrain the solution. We're going to constrain the solution space, encode those constraints into the neural network, and things will get better somehow. Now, this is just an illustration of what an equivariant function is. So equivariance basically means that the function f commutes with this group operator. So that's that equality at the lower right-hand side. Okay, so invariance means that it doesn't change with respect to the group operator. Equivariance means that it commutes with the group operator. The policy, so here, this is like segmentation. So you can either, starting up the upper left-hand corner, you can segment and then rotate the segmentation, or you can rotate the image and then segment the rotate. Either way, if you have a good segmentation function, those should produce the same answer. So we know that the segmentation function that we're trying to learn satisfies this constraint, and as a result, we don't lose anything by encoding that constraint into, let's say, the neural network that's trying to do semantic segmentation. So same idea, but we're going to apply it to policy learning. Okay. So I assume everyone's cool with this so far. Next step is we're going to talk about the mechanics of actually encoding symmetries into the neural network model. Yeah.
Last one, I thought you said, is the transition function equivariant or invariant?
The transition function is invariant. When the transition function is invariant, then the Q function is invariant, the optimal Q function is invariant, and the optimal policy is equivariant. So, I illustrated what the transition symmetry meant. You know, for the Q function, like if we were to rotate the world, then and we rotate the action, you know, the value of that rotated state in action should not change, would be invariant. You know, it's like a scalar. You know, the action is like it's that. That's right. So this is just like the transition function. We rotate both of the parameters of the function. Yeah. All right. So again, our strategy is we're going to hard code the structure that we know exists in the Q function and the policy. We're going to code that into the neural network that we're trying to learn to represent those things. And the question is, okay, how to do that? How do you build a neural network that encodes those constraints? So I'm going to give like a very simple example that hopefully conveys like some aspect of like how this might possibly work. So you know, because we're working with this rotation example, imagine that we're in the group of planar rotations here, SO2. Now, there are certainly methods for thinking about SO2 directly, but it's kind of annoying to tell you about. So I'm going to tell you about, instead of that, I'm going to tell you about the cyclic group. So the cyclic group is a subgroup of SO2. All right, so people know what this is. So cyclic group, you can think about it as the group of rotations by 90 degrees. So the cyclic group it's an abstract algebraic group. So all right, we'll just pretend we're on this slide. It's an abstract group, meaning that it's just something that you apply an operator to, and if you apply that operator like 4 times, it like returns to identity. That's literally the only thing that cyclic group. I mean, it just happens that rotation the rotation can be modeled that way, and that's what. So you have the abstract group there at the top, the cyclic group, and there's 2 representations that, one representation on the left is like the standard rotation representation of orientation. It's like a vector in the plane. And in that representation, rotation the rotation operator basically amounts to a rotation matrix, which is that 2 by 2 matrix there. Now, you don't have to represent the cyclic group as a rotation, because like it's this abstract algebraic group. You could represent it as like a one-hot vector or something. And in that case, like a one-hot vector indicating which of those 4 group elements you're at. And in that case, rotation would be achieved by this permutation matrix here on the right. Okay, so on the left, we rotate, we have a representation where it gets rotated by 90 degrees. And on the right, we have this cyclic shift permutation matrix. Both of them valid representations. You might ask, why am I telling you about representations of the group C4? And the only reason is because we're going to build a neural network that's going to have these representations inside of it. So let's look at that. Oh, before we go too much further, I need to credit my collaborator, Robin Walters, who's a who basically introduced me to all of these ideas in equivariance that we're talking about here. So, and most of this work is co-published with him. Okay, so back to the neural network. Let's think about how to constrain a neural network to encode only equivariant functions or invariant functions. All right, that's what we want to do. We want to build a neural network with trainable parameters that is only able to represent functions that satisfy these symmetry constraints that we're able to define. All right, that makes sense. Our approach is going to be to constrain each layer to represent only equivariant functions. Okay, so if each layer is an equivariant function, then the whole thing gets to be equivariant as well. All right, so for the sake of argument, think about this layer M2. So this thing here is an MLP, which is basically a series of these matrix multiplies interspersed with nonlinear activation functions. Okay, we know that. MLP matrix, I apologize. Matrix multiplies, and then we multiply by M1, nonlinearity, rho, sigma 1, M2, and so on. Okay. So we want to constrain each of these layers to be to satisfy the equivariance constraint. What is the equivariance constraint? I've written it right here. So we have, and this is just for this layer M2. Okay. So we are going. What we want to do is we want to find a constraint on the matrix M2 on the parameters that we're going to learn. M2 is a parameter matrix. We're going to constrain the parameters that we learn in the matrix M2. Thank you so much. And we can constrain them so that they satisfy this constraint. And that's actually not too high. That's like a linear algebra problem or something, because row 2 and row 4, those are defined there at the top of the screen, right? So all we need to do is solve for an M2 that satisfies this constraint, and you can do that using like an SVD or it's really linear algebra, and there's what you get. So all M2s that satisfy this constraint have the structure shown in the matrix shown in the middle of the top of the screen there. You see there's only two free parameters, A and B. Okay, so what we're going to do is we're going to use weight tying to tie those to tie those parameters together. So if this were an unconstrained MLP layer, this would be a matrix of 8 unconstrained parameters, and we'd be doing SGD, and we'd be learning those parameters. And here we're going to do a weight tying arrangement where we tie the parameters in the manner that's shown there. And we're still going to do SGD, but those weights are going to be constrained to be to be tied. All right, so that makes sense. Yeah.
Do all forms of enforcing equivariance effectively come down to some kind of type, or does it get more complicated?
No, all the things that people do today basically amount to weight tying. Now, we want to build equivariant models. Our approach is to create equivariant layers. Is it necessary to do that? Not necessarily, but that's sufficient. Yeah, okay, so there we go. So that's it in a nutshell. So, and I guess the other thing to mention here is that you notice that there's like R2 and R4 there. So the R2 is like a representation. So I think to kind of recognize here is that we are encoding, normally in a neural network, you're encoding like kind of arbitrary feature vectors. Here, we're encoding, in this case, just a single feature, a single, like a single feature element, but that feature element has like, has like a rotation associated with it, or in this case, like a direction, since this is like a rotation in the plane. Yeah, and in the layer, in this layer, that vector is represented literally as a 2D vector, and here it's being represented as like that permutate that one hot vector that's getting permuted by the permutation matrix. So different representations of the same group element, the same algebraic group in the neural network. But regardless of the representation, these constraints are gonna be enforced at each step. Generally, the interior layers of the neural network are going to have these regular representations, which is a permutation representation, and then we might transform into, just because it's a convenient thing in terms of feature representations, and then we're going to transform to some sort of more geometrically meaningful thing at the output. Yeah.
Reducible representation or large vectors?
This thing, you're always using, inside of the neural network, you're using, or at least this is what they do today, they're using irreducible representations. You kind of have your choice about what, which choice of irreducible representation you're using, but but you're doing something there, and that's kind of, that representation is associated with each of these layers. All right. So one perspective on this neural network learning thing is something like this, where we're constraining the search space. So the big bubble is, the big ellipse is all the neural network functions, the parameter space that we would typically be faced with. We're enforcing structure, and we're reducing the search space. So, pretty common picture, I think, that you see in AI. Here we're applying it to learning, and learning is going to become faster and more data efficient, and it's going to generalize better. Okay, so now what I'm going to do is I am maybe going to apply this to grasping. So what I'm going to do is I'm just going to apply it to a series of problems, robotics problems, because it's kind of what I do. So here we got grasping. So the grasp problem that we're addressing here is the simplest problem I could think of, which is why it comes first. We have a neural network which takes as input a top-down depth image of the scene. It could be an RGB image, but here's the depth image, and it outputs a grasp pose. And a grasp pose here is in the form of x, y, theta. All right. So give it an image. It tells you where to position your hand in order to grasp, and then it's like you use a value in the depth map or something to figure out how deep to go. All right, makes sense. We want to learn that function. So a good grasp function is going to output poses such that if you were to move the hand to that pose and close the finger, that you would grab onto something. Let's see. All right. I think because the video's there, it's like it went right there. All right, so we're learning that function, and the only thing we did was we encoded, we constrained the network to be SO2 equivariant, basically using something very similar to what we just looked at. Instead of using MLPs, here we're using convolutional layers. Instead of using C4, we're using like some larger group that's got rotations and reflections and whatever, but a finite group. And what's cool about this is that changing the neural network made this thing much more sample efficient than it is otherwise. So we've structured this. So this is a grasp learning problem. We structured this thing as a bandit problem. So the bandit problem is actually a contextual bandit problem. So the contextual aspect is that you're giving it an image, and then it has to, the arm that it's pulling is like the location of where it's trying to grasp. And at each trial, at each arm pull, this thing executes a grasp. And your idea is to maximize the accumulated reward over these trials. So, so contextual bands is like a simplified form of reinforcement learning. You get it? So what this thing is going to do is it's going to it's got a randomly initialized neural network. It's going to execute random grasps, and it's going to collect data as it's doing this grasping. And over time, it's going to learn a good grasping function. And as it does that, its grasp success rate is going to increase.
How do you measure your success? Oh,
You check whether the finger's closed all the way. Yeah, so it's just grasping anything here. Maybe there's some, maybe we're interested in a particular object, but that's not what we're doing here. Yeah. So what's cool about this is that it learns to grasp on physical hardware, like in about an hour and a half. There's no other system that can do this. So most of the time when people do grasp learning, they've got like a simulator and they run it, and you're at NVIDIA and you call like Isaac Jim, and it's like, here's a bazillion grasps, and we train our model. We have like, this thing got 600 grasps and it learned a function. And how is it able to learn a complex grasping function using such a small amount of data? It's because we structured the model. We did, is like reason, are we breaking anything to structure the model? I mean, possibly, yes, but I mean, this is structure that kind of exists in the domain. Like if we do have this top-down image, then, and maybe we don't have that, maybe that's violated, we can talk about that. But, in this context, like it makes total sense, it's satisfied, and it helps like immensely. So we got some alternative methods there. Those are the other lines. We're the one on top. Yeah.
What is the symmetry that you're expecting? Because it seems like if the input's the image, then my equivariance with respect to if I were to rotate my camera, I would continue to do well. But it seems that for you, like physics itself is equivariant, is invariant to the rotation. So like, what is the symmetry?
So the symmetry, like if you were to express it physically, the symmetry would be that if it had one of these grasps on a particular scene, and you were just grab the bin or rotate the grasp, that you're constraining the model to view those two grasps as equivalently good. Okay, so another way to say it is that if I have an image of my iPhone or something, and the image of looking down at my iPhone and having my hand in this location is equally good by this constraint that I've imposed as a rotation of 90 degrees of the image and a rotation of 90 degrees of my hand. Okay, so the constraint is exactly what we showed in those introductory slides where there's the pushing. Right. So you remember with the pushing, there's like pushing down and pushing to the side, and those are the same thing. It's the same thing here, except instead of pushing, you're grasping.
Here you never working with that. So why I'm trying to understand why it's common.
Yeah, because these objects are deposited into the bin randomly, and they might appear in any orientation. So in order to learn a good grasp function, you need to learn how to pick up these objects in any orientation that they appear in, or in any translation they appear in. And this is like automatically generalizing. I'm very glad you answered that question, because I don't want to have that kind of ambiguity lying around here. Yeah. Yeah. Yeah, data augmentation. Shouldn't we be doing that? Yeah, that's an excellent point. Let's see if I can, do we see that? There it is. Okay, yeah. There's two other approaches that I generally think about when, in terms of alternative ways of leveraging a symmetry constraint. One is data augmentation, another is canonicalization. Canonicalization is the idea that you're going to somehow figure out what the orientation of the stuff in the environment is, and you'll learn a representation that's registered to that object representation. And this method works better. First of all, it's not an either or. So in the work that you just saw, we're also doing data augmentation. But at a high level, these three methods are leveraging the same insight. But like under the covers, they're doing slightly different things. Like first of all, The equivariant model is applying a lot more structure. There's fewer parameters to learn. The equivariant constraint is embedded at each layer. It's encoded into the model. So in data augmentation, you're saying, I know the constraint exists. I'll use that to give me more data, and my model will learn. You're still asking your model to learn that this equivariance constraint that you would have otherwise been encoding. So, like, you're leveraging the same insight, but those methods work different, and that's reflected in like the actual performance. So these this VPG is basically a data augmentation approach. Yeah.
Did you ever run into problems with sort of like configuration spaces not being reachable? Because I feel like you can grasp an object from this way, or I can turn my arm around and grasp it this way, and the model should see those two as the same because of the
Yeah, but they're not the same if they're not reachable.
right.
That's an excellent point. Yeah, this model totally breaks in that situation, and that's something that, it's something we're looking at. I mean, this only, like, a couple of answers there. First of all, equivariant models are surprisingly robust, resilient to mismatches in model symmetry versus domain symmetry. So it doesn't have to be perfect for you to benefit still a whole lot. And we can talk more about that. But that's an excellent point. I mean, this thing about the workspace is, if there's whole regions that are just unreachable, then it's potentially problematic. Yeah.
Like 90-degree rotations.
Oh, that's an excellent question. Yeah, the question was whether we were doing 90-degree rotations. No, we were so the model was constrained actually with D8 or something, which is a dihedral group with 8 rotations. But there's a distinction between the symmetries in the model and the rotations that your robot can. Those are distinct things. The symmetry in the model is telling you something about the mechanism for generalization, which is distinct from the action space. Now, because it's distinct, you're going to have to learn. It's not perfectly generalizing over orientation. It's only generalizing over that finite group. Now, there's definitely approaches. There's approaches to, you could enlarge the discretization. You could take different irreducible you could represent the rotation in different ways. Ultimately, it's like a finite. You have some finite mechanism, so there's going to be some possibility for error.
Is there a way to represent them?
Yeah, you would use circular harmonics, and you can very similar kind of like presentation would you could do there. Yeah.
So for the objects that
Or spherical harmonics, or Winger D matrices is you can extend that idea. Yeah, I'm sorry.
for the objects that are visually not the same after rotation, but would be like probably pretty similar in terms of shape after rotation, well, the robot learns to rotate, like, for example, like it's like
It generalizes how you would expect like a standard convolutional model to. It's going to accommodate like variations in shape. It's it accommodate even if there's like mismatch between like domain symmetry and the actual model symmetry. It's pretty resilient. Okay. Oh, you can see that. Okay, good. Okay, we did that was our we applied that to grasping. All right, you saw that. Now we're applying it to reinforcement learning. Here we're applying it to SAC, soft actor critic. Same idea. We're going to constrain the actor and the critic using the same mechanism. There's some additional details that I will not bore you with about like the variance and whatever, but that is the variance outputted by like the policy. I should say, keep in mind, it's not just rotation. It could be reflection. It could be, it could potentially be other stuff. All right, so it helped with grasping significantly. We were able to do stuff on a robot. It helps even more with reinforcement learning. Why does it help with reinforcement learning more? We're doing bootstrapping. So reinforcement learning classically does something called bootstrapping, where you learn the value function a little bit, and that helps you learn the value function some more. A little bit of improvement in the data efficiency of the underlying neural network model speeds up reinforcement learning significantly. So here we have the blue line at the graphs at the top. The blue line is us. The other guys are down there at the bottom somewhere. These are actually, so we have Dr. Q, we have Firm, which are, these are baselines from 2022. I don't think things have changed hugely. Same results here. Well results. So it works like just really, so it's so efficient that we can actually just do reinforcement learning on the physical robot. So here the state space is the image, just like before. Now we're outputting, but before with the grasping, the actions were x, y, theta. Here the actions are displacements and rotations of the hand, okay? The hand is still constrained to point downward, but we're doing displacements in x, y, z. So it's like a four-dimensional action space, if you will. And this is like, the policy network and the value function are like, they're initialized with like random numbers, okay? So it's not, we didn't like transfer from simulation. I mean, we could have transferred from, in the paper, of course we did. We evaluated, tabular rasa learning versus training in sim, and then trying to transition, trying to do, copying the model to the online setting. But even in a tabular rasa setting, this thing learns like quickly enough to be able to learn tasks like this in about an hour, 45 minutes for depending upon your task. And you can see here it's learning to grasp. And say one of the behaviors you see is it just keeps like moving its opening and closing its fingers, which is honestly like if I were trying to learn to grasp, it seems like a pretty reasonable thing to do. Reward in this case is achieved by picking something up by a certain amount, and that's measured by how far the fingers are apart. Same story here. Here we have to pick up an object and stick it in this bowl. Again, we can learn directly on the physical system. Now you might say, why are you learning on the physical system? Learn in simulation. Just, so first of all, obviously, like if you learn on the physical system, it solves a whole bunch of problems in terms of domain shift between the simulated system and the physical robot. So for example, I have a video, I'm not showing it, where it works really well on transparent objects. They're visually hard to simulate. There's also domain shift in the mechanics of actual grasping. And one of the things we see is that in some circumstances it's actually harmful to train in simulation because you're learning the wrong things, the wrong strategies. Small imprecisions in the behavior of contact and manipulation, in simulating the behavior inside of the simulator can cause bad behaviors and lessons to be learned by your model to have to get unlearned when the thing actually goes and attacks some real world problem. So I think that the idea of learning using reinforcement learning on physical robot hardware is not something that you can like pretend you're not going to have to do. At some point we're going to have to do this. Our robots going to have to adapt to actual physical environments. All right, last thing. Well, I don't know, maybe not the last thing, we'll see. Continuing on, diffusion policies are all the rage. Oh, you can't see it, all right. Diffusion policies are all the rage these days. So naturally, it jumped into our minds as well. So diffusion policies are, about I don't know how old is it, I don't know. It's about 1 year old. The idea is that you're going to use a diffusion model to do behavior cloning. So behavior cloning is basically imitation learning. So we're going to get a bunch of demonstrations, and we're going to learn a model that reproduces those demonstrations. Now, one of the challenges in behavior cloning is accurately modeling a multimodal policy. That's generally not a problem in reinforcement learning. Does anyone know why? This multimodal thing? It's a big deal in behavior cloning, not in RL. RL doesn't care which mode it learns. It just learns one way, and it's like, I'm good. So, RL generally learns one way of doing it, not necessarily all the ways of doing it. Hence the the actor, in order to perform well, it doesn't have to represent these things. But, you can train yourself. You say, I'm going to learn from like a boatload of data and it's multimodal data, and you need to do a good job averaging, a good job doing that model. And diffusion models, there's kind of two approaches that folks have explored in this context. And one is energy-based models, the second is diffusion-based models. Both of them do a good job modeling multimodal functions like this. Diffusion policies, at least the conventional wisdom right now, is that they're a little easier to train. We'll see, we'll see how far that goes. In any case, we are going to do our equivariant thing with the diffusion policy. So in the diffusion policy, instead of learning the actual energy model, what you're doing is you're learning this denoising function, and that's what I've circled in some shade of magenta over here. So we're learning the denoising function, and obviously we're going to constrain the denoising function to be equivariant. You can see my proper. All right, so yeah, this is pretty self-evident, but if the expert policy is equivariant, and we know it is because of the result we showed before, then the denoising function is also the denoising function from the optimal policy is also symmetric. So we're going to constrain the denoising model, and when we say we're constraining the denoising function to be symmetric, like this is like a visualization of that. So these vector fields here, that's like your denoising function. So your denoising function is moving around all of. So I guess I didn't say this, but where we're doing diffusion policies, I don't know how much you guys care, but when you're doing diffusion policies, the way this works is that you start with like a collection of these little dots on the left that represent via points on some trajectory, and you iteratively denoise them so that those via points all end up at the correct spots along some trajectory. That's what I'm trying to visualize on the right side of the screen there. And this thing proceeds in a series of so-called denoising steps. Now, each denoising step you can think of as pushing around those little via points according to some vector field, like that vector field. So the denoising function is basically a vector field, and when we say we're constraining the denoising function to be equivariant, what we mean is that the vector field is going to be symmetric with respect to the input image and with respect to the input image. So the vector field is essentially, those are the actions. So before we were talking about equivariant models, we were like, the transition function, we had states, we're going to rotate the states, and the actions, we're going to rotate the actions, and like the policy was going to be equivariant. Here, we rotate the state, the input image, we're going to rotate the vector field, that's the actions, and those are going to, those things are going to be equivariant. So that's our constraint, and all right, you might not be able to, can you see the model? There's the model. Okay, so so we constrain the encoders to be equivariant, and then we propagate the irreducible representations, if you will, through the denoising model, the actual denoising model, which is like some kind of a 1D convolution, and then it produces this denoising thing. All right, roughly good. I know I spoke quickly. All right, let's see the video. So this is cool. So by the way, so this work, we actually ran these, we developed the idea at Northeastern, but we ran these experiments, these hardware experiments at BDAI, because, it's a cool place to be. All right, so what's cool about this is that we trained this with only 60 demonstrations, or 58 demonstrations or something. So what we, by virtue of using these equivariant models, we reduce the number of demonstrations required to learn a good policy. So if we're talking about reinforcement learning, then data efficiency corresponds to really nice looking learning curves. If we're talking about imitation learning, data efficiency corresponds to reducing the number of demonstrations, expert demonstrations you require in order to learn a behavior effectively. So here, if you're using the off-the-shelf models and you look at, I don't know, whatever the diffusion policy paper is, you would need 200 or 300 demonstrations in order to produce a behavior like this. So here we're, we're reducing that maybe by a factor of 5 by getting down to about 60 demonstrations. Yeah. Is the embodiment and effector space? Yes, the action space is basically displacements and angular velocities for the end effector. Yeah, so there's some sort of, and it's actually, you can see, if you look really carefully, if you had looked really carefully, you notice there are these little green lines in the visualization that they were illustrating the trajectories generated by the diffusion model. So it's generating trajectories in this, essentially in a twist space for the end effector twist space. Yeah, so this is super cool. I mean, you ask like, where do we want to get with imitation learning? Well, it seems like we want to get to a place where we're, giving this thing like 1 demonstration, like 5 demonstrations. Well, we're not there yet. It's like 60 demonstrations, but like this is not an unreasonable behavior that we're trying to achieve. And so if you're at BDAI and you're like, we want our robots to learn these cool things, like if you're willing to put, if you're really motivated, you can like, put in a bunch of effort and like create a bunch of demonstrations, and you say, well, maybe it doesn't matter whether I have to give my model like 300 demonstrations versus like 60 demonstrations, but I mean, I think it matters. I mean, it's like super annoying to make these demonstrations. It's like, yeah, you can try to improve the demonstration equipment, which is all cool and everything, but I mean, I think we want data efficiency here. And, and what's cool about this is that we're not, there's all sorts of other things that could be done, like, in orthogonal directions, like we could go train RT2 or something on a pile of X embodiment data and try to get some intelligent priors and try to bring that to bear. And that like is totally compatible, this thing with the symmetric models, like you can virtually take whatever you're doing and just drop out what your neural network model is for an equivalent symmetric model. Now it requires a little bit more thinking about like, well, what is a symmetry? How am I going to encode it into this model? But it's not like, it's not like inconsistent. It's compatible with just about anything that any kind of like machine robot learning approach that you might have in mind. The last thing that I will point out, which I don't have a lot of time to do. Well, I'll show you the results. The results are good. So if you have the baseline non-symmetric model and you're trying to do this bagel thing, 10% success. Our model, 80% success. This is on like the 58 demonstrations. And the other results are kind of similar. Yeah.
Are there tasks where symmetry hurts? Because,
That's an excellent point. The question is, are there tasks where symmetry hurts? Yes. We have our upcoming NeurIPS paper where we, actually, let's look at this slide first. So imperfect symmetries. So question is, like, we could benefit from symmetries. In robotics, things don't always go according to plan. There may be model mismatch. That is, the symmetry in the environment might not match exactly the symmetry that you just finished encoding into your model. What happens then? There's 3 situations you could be in. Like you could have correct equivariance, perfect match between the model and the environment. You could have incorrect symmetry. That is, the dynamics of the model or whatever function you're trying to learn is precluded by the constraint that you encoded into the model. So it's impossible for this model with those constraints to fit that function. Okay, that's incorrect equivariance. And then the thing in the middle is extrinsic equivariance. So extrinsic equivariance is a situation where the real world might be out of domain for the thing that you trained your equivariant model on. So one of the questions you have to ask is like, well, what happens when what happens when there's a mismatch? And the answer is generally the best that can happen, the best thing that could possibly happen does happen. So if it's incorrect, and if your model precludes learning the function that you need to learn, you're in trouble. You're done. It's obviously mathematically impossible. If you're any other situation, the equivariant model is probably going to help you. And in particular, an example that we often encounter in robotics is this situation where instead of having a top-down image, you're looking at it from the side. Most of these robot learning examples have things learning from looking from the side instead of from the top. That's an imperfect symmetry as visualized here in the middle, in the sense that a rotation of the image is like, it's not exactly the same as like a rotation of a top-down. The domain is not like equivariant with respect to that kind of rotation. The model the imperfectness here hurts, but the symmetric model helps a lot. So you have two interacting forces here. One is like having the structured model is making you much more data efficient. Having the mismatch between model structure and world structure is hurting you. And usually it helps more than it hurts, unless you're in a case where it's mathematically precluded. I think that is just about all. I have one final kind of illustration of, we did something super cool with a 3D extension of something called transporter network that is super cool and uses Wiener D matrices and is like super sample efficient. It's like crazy sample efficient. It's symmetric models. It's like 1,000 times more sample efficient than a baseline transporter net. It's like you can learn like meaningful tasks in 1 to 10 demonstrations. It's kind of nuts. So we extended this kind of approach to a 3D setting, and there's some complexity there. And we're using these Fourier coefficients to represent orientation instead of the discrete representation. But the results are really good. Outperforms RVT, Robot View Transformer, which is kind of a current NVIDIA thing by, a significant margin. So that's it. Yeah, thank you very much. Is big in? Maybe, but I think you should also think about adapting to your own data.
So you enforce the equivariance or the invariance in a kind of rigid way. Your model needs to be equivariant every step of training. An alternative that you could consider is, penalizing how invariant each layer is. Have you guys tried that? Does that not help?
That's interesting. Yeah. So the comment is, what happens if you want to, is there a soft version of this equivariance constraint? I guess, so this is something we're very interested in. We think about it in the context of approximate symmetry. So you have a hard symmetry constraint, approximate symmetry constraint. So my collaborator, Robin Walters, has been the one who's thought about that more, although, I worked on that more, although, I certainly want to be doing that. The mechanism right now has been to take a convolution kernel with hard equivariance constraint and basically add some wiggle room to it, in the form of a bias or some additional parameters that get added onto the kernel. So take a constrained kernel and add on some additional free parameters, basically. So the free parameters would accommodate variation outside of the symmetry constraint.
Do you analyze free parameters during training, or do you just, if it's true symmetric, you don't train?
I am not sure. I don't think so. There's some other ideas out there too. So another one that comes to mind is this idea that if your domain has a symmetry, but that symmetry doesn't necessarily exist with respect to the observations. It might be possible to learn a function that projects from like your state space or your action space onto the space in which the function is actually equivariant. So you could have a non-symmetric portion of the model, you can have a symmetric portion of the model, and you know, and under certain circumstances that can be an effective thing to do. Great. Let's learn on real robots. Did you have a question?
Maybe a following question, but I was just, sorry, I didn't.
Oh, it's okay. Yeah, I just, if you need to leave, you can leave. That's all I meant to say.
So usually kind of bigger is better, meaning given a particular model value, model class, like with some particular symmetry, say, actually, if you can train a larger model, you would rather train a larger model. For example, it's like just with the MLP, you just.
Yeah, I get it. I agree. Yes, larger, bigger is better. I agree with that. I think that it still holds here. So.
Right, a bigger one, sorry, a bigger model with the symmetry built into it is probably better.
Yeah, I think that I don't think there's anything contradictory. I mean, like there's like in principle, it seems like kind of contradictory, but like, let's say, you know, we were building like ResNet 150 or something, like, you know, we would still be doing that. We just constrain it,
Right.
you know, or do it in our transformer or whatever, you know.
Do you have a thought about, well, because there is some notion that the symmetry constrained model is somehow lower dimensional, even though you may have wanted to put the same.
It's lower. It's yes, there are fewer free parameters in the sense that the parameters that otherwise would have been free are tied together. Now, when you're doing SGD, it's essentially the parameters that are tied together. Obviously, the gradients for those parameters get added together. So it doesn't. This doesn't seem to affect like the dynamics of SGD in a bad way or something. At least not so far. You know, but it's like a lot of deep learning. It's like, you know, your knowledge may vary and you have to try it out. Like, you know, what sort of irreducible representation should you be using? Like, should you be using this discrete subgroups, you know, discrete groups? Like, that's like a really effective thing to do. But, you know, or the alternative is like, for example, circular harmonics to represent orientation. Either, you know, two irreducible representations of the same or approximations to the same to the same group, and those things can perform differently because they represent, you know, there's different things going on in the model, and you know, we generally find that these discrete groups when they're applicable are just really effective. But I don't know, but they're not. But anything out of 2D, they're not really applicable. I don't know. All right. Have a good one.